Okay. Okay, so I want to first touch on a couple of comments that came up on Thursday. Number one, I mentioned that when you're fitting data that's affected by a big perturbation, it's going to be problematic for ARIMA and ARIMA, those functions, and that's because they are fit to stationary data. If you have a big perturbation in your data, they're not stationary. The second point is when you're fitting these seasonal ARIMA models, it's, as I mentioned, you're modeling, say, the effect of last February on this February, or does last February give information about this February? And often when we're working with population data and we're thinking about, okay, does the size of the size of the recruitment, you know, how much spawning was there this year? We want to know how that reproduction affects the future population size. And in that case, these types of models wouldn't work because it's not, you know, the effect of February on February, March on March. It's the effect of, you know, this, you know, total spawning size and, you know, whatever the breeding season is on a number of future years. And the way you set up those models is that you use the, say, the spawning size as a covariate. And then you can have that covariate affect multiple future years or multiple months in the future year. Okay, and then another big point somebody asked, is removing the mean season the same as a seasonal difference? And no, it's definitely different. And think about that example where the season is like increasing like this. And if I subtracted off the mean season there, then I would still get a seasonal cycle that was big on this end, and then it's smaller on this end because those seasonal cycles are big here and they're small here. And I didn't mention this, but it's something important to know, is that if you have data with multiple seasons, so that would be like you had, let's say, daily data, and you had a monthly cycle, it had something to do with, say, the tide cycle, and then on top of that you had a yearly cycle. So this would be really common for us, right? If we had monthly, or if we had daily data and it was working and it's in an ocean environment, it would be really common that we have a monthly cycle having to do with tides and a yearly cycle on top of that. If you have that kind of data, it's going to be problematic for the standard seasonal models. There are ARIMA models that you can apply that have multiple seasonalities, but it's not the standard stuff. Okay, great. Move on. Okay, so let's go into something new today. We're going to start talking about state space models. So now models that have observation error. So far, what we've been working with, these ARIMA models, they don't have observation error. It was like we're modeling a process where we're modeling the value, our observation, as a function of the observations in the past. But now with state space models, we're going to back up and say, well, our data are observations of an underlying process, and our observations have error. So we can't, or we don't want to, directly say that our observation is a function of the observation in the past. We don't want to do that directly because there's all this error in there, right? So the observation in the past might have been really low, not because the population size is really low, but because, I don't know, the river was really cloudy and we couldn't get very good measurements, right? So it was low just because of observation. So we'll be talking about this class today and on Thursday, and then we'll move into model evaluation and selection, and then we'll start talking about how you can fit this class of model with nonlinearity and non-Gaussian errors. And once we do that, we'll start really digging into, okay, let's do some ecological analyses. Okay, so this is about the most simple state space model that you can come up with that includes a random walk. We have the X part is the process. So there's something that we're observing, and it's a random walk. So that's a random walk right there. You see that time dependency there. X at time t is a function of x at t minus 1. There's no b term in front of there. So since you just see that term appearing without any parameter in front of it, you should recognize that that's a random walk. It's just going to kind of wander off. And it's got this u term here. And what that means is it's going to tend to go up if that's positive. It's going to tend to go down if it's negative. So that's our process. Our process is a random walk. But we don't see that. It's hidden. What we see are the y's. And the y's are the hidden process plus some error. So we observe the hidden process, but it's obscured by error. This class is extensively studied in economics, engineering, and these are 3 textbooks that all of us have on our desk. These are some of the classic ones, but you'll find this lots and lots. If you just Google state space and textbook, you'll find many examples. Yes.
I think probably all of these are listed on the class website. Yeah. Under the references.
This is the main one I use. I think you mainly use that one. You use that one more. No. No. Okay.
Both probably equal.
These are, so I told you the X's are your process. And here are three of the simple process models that we've been looking at so far. And we'll be playing a bit with these today. So that's the random walk I was just showing, and it's got the trend. You could also write it this way. Only thing that's changed is it's t plus 1 and t. I note that because in many textbooks they write it that way. This t plus 1 is exactly the same model. This is missing the u, so there's no trend here. And then the other one is this one where we have this b here, and if that b is between minus 1 and 1, then we have a mean reverting process. It's going to be something that's kind of going up and down around the level. Okay, in ecology, this model is also called the Gompertz model, and it's one of the models of a density-dependent process. And if you look in ecology textbooks on density dependence, you probably see the model written as the top. So N is population size, and population size at time t is some function of the population size at t minus 1, and that beta term is indicative of the strength of density dependence. So density dependence is the tendency to return to some level. So here's an example. This is B is really close to 1. I think this was about B is 0.85. And you can see that this process, and this is a population size, is kind of wandering. It does have a level, about 1,000, that it's fluctuating around, but it fluctuates weekly around that. And this one, B is about, I think this is about 0.2, and you can see it's fluctuating very tightly. This type of model has been used a lot in studying marine ecosystems and freshwater systems, and looking at especially plankton dynamics. And I'll talk about that at the end, in using this class of model to try to understand how plankton species are interacting with each other. But the density dependent part of that, how that the species is infecting itself, is that model right there. Okay. One thing to know about this class of model, which we're going to be using a lot, by the way, is that it can be hard to fit. And the reason that it can be hard to fit is that the B and the U parameters, so this is your strength of density dependence, and this is this parameter that is, it can be interpreted biologically as like a, I don't know, sometimes it can be interpreted as a population growth rate. Not exactly, but kind of. But more, when it's written that way, it's going to affect the level of your data. But the problem is if you were to plot out your likelihood surface and you had B and U, you would see that there's a peak, but there's also this big ridge in the likelihood surface. And whenever you have ridges in a likelihood surface, you have an algorithm. It doesn't matter what algorithm that you're using. It doesn't matter if it's frequentist or it's Bayesian. When you have these ridges, the algorithm is going to get kind of lost on the ridge, and it's really hard to find a peak. And you need a lot of data. So with this class, what we're going to be doing, you'll see the examples, we're going to be doing some tricks to get rid of that parameter, so we don't have to deal with that. Okay, so I mentioned on Thursday that random walks are really important in the biological and ecological sciences. And so some of the problems where this class of model comes up is movement models, said gene frequency. Another example would be somatic growth, where the growth is by fixed amount. So that would be like an additive random walk. We can also have these multiplicative random walks that look like this. So it's a random walk because we have the n at time t is a function of n at t minus 1. And this is going to come up in population growth. So this right here would just be exponential growth. It also comes in somatic growth, if the growth is by a percentage. And if we take this model and we take the log of that, we come back to that model. The errors in these models are classically assumed to be normal. You don't have to do that. People will look at models where you have long tails, and that can have some really interesting effects. You can have things like suddenly jump to a completely new value if you have these long tails. But classically, it's assumed to be normal, and you can think about that as, like, let's think about population growth, right? And the population size next year, it's affected by a whole bunch of little perturbations. Like, what was the survival from today to yesterday, from yesterday to today, today to tomorrow. It's all these little bitty perturbations. And if you take the average of a whole bunch of little perturbations, you're going to come up with something that's normal. So that's kind of the sort of back of the envelope reason why we often see, well, why we assume normality, but also if you look at the differences, when you estimate these models and look at the differences, that you often see the errors look about normal. So here's a plot of a whole bunch of different random walks. And the thing to note about this is that these were all simulated with exactly the same parameter values. And it was, on average, a slight decline. And the variance was pretty small. It's not a really big variance. This is pretty typical if you were to fit a model like this to some population data. It's pretty similar to the variance that you would estimate, something quite small. It's a variance of 0.01. And so you can see that with the same parameter values, you can get very different trajectories. And I point that out because, you know, when we look at data and we have this, and you look at that and you're like, wow, something really different happened. Perhaps my whole system changed here. And when you should recognize, however, that if you're fitting it with a random walk, that's not necessarily the case. That your system, the sort of the underlying structure of the model could be very much what could be exactly the same for this versus this, and the only thing that's different is it just so happened that the error terms were, they must have been negative here for the few times steps, right? And then they're positive here, so we'll back up. But the structure of the model is exactly the same. The parameters are exactly the same. We're going to run into this when we start working with real data and we quantify our uncertainty. So if you look at that, you should have this sense of like, oh, yeah, there's probably, you know, if one set of parameters can produce all of that, then some, you know, another set of parameters that's just slightly different could also have produced all these, or something that looks kind of similar to this. And so it shouldn't surprise you when we show you the uncertainty about our parameter estimates, that they're going to be pretty wide often. We're going to need a lot of data to estimate some of these parameters. Okay, so I talked about that. So let's see some examples of, let's go back here. Okay, so I've been talking about the state process. Now we're going to talk about the observation process. And this is something that makes working with ecological data really hard. It's kind of unique to us relative to other areas of science where we can do an experiment and we can understand in great detail our observation error process. For example, we can repeat our experiment over and over. If we have a temperature gauge, we can stick that temperature gauge in a known temperature and know what the error rate of that temperature gauge is. But when we're working with ecological data, fisheries data, we often are not able to know exactly what our observation errors are. Okay, so here's an example. This happens to be monk seals. And then here I want to show you another example. This is the one I wanted to show. So this is an example of observation error in real data. This is an actual survey photograph for stellar sea lions. I worked for many years on stellar sea lions. And this is a real photograph taken from an airplane. And now we're going to go and we're going to count all the stellar sea lions here. So you can see, obviously, we're going to have observation error. And it's not just the fact that this is a photograph and it's fuzzy and the sea lions are kind of half on top of each other. We got that problem. But we also have a problem that there's sea lions on the other side of that island that we don't see. And there are sea lions in the water, and we don't see them either. Right? So we have all these different sources of observation error, and we don't understand, we're not going to be able to understand the magnitude of these and how they're changing with the, how our environment is changing. Right? So for example, we have sea lions in the water. What is driving them into the water? Well, the food. Right? So we have some variability in the food that they're going out to forage for. And we don't know, how close that food source is to this island. If that food source is very close, they don't have to spend a lot of time in the water. And if it's farther away, they spend more time in the water, so there's fewer of them on the island. So we have those kind of things that are adding all this variability to our data. And we can go out and we can do things to understand our survey variability, right? So imagine, instead of having a survey like this, imagine that we have a ship survey and we're going out and we can think about experiments that we might do to understand what our standard error of our population estimate is, or a survey estimate is. But there's going to be all these other things that affect citability that we're not going to be able to do an experiment on. So it's just like fundamentally that it's different for us, that we have to estimate the observation error variance. We just are not going to know fully what that variance is and all the different components. Okay, so let's see some examples with some data. And let's start getting a better sense mathematically what observation error is. So let's say that these are our population counts. We have 20 of them, and now we're going to fit a model. So we're going to start by fitting a linear regression model. That model is, we can still frame that as a state space model, but what we're going to say is that our state is this straight line, and now our data are this part here. This is our state, and our data, y, are our state right there. It's deterministic plus some error. So I've written this just as one equation, but you can think of this as two. The xt equals alpha 0 plus beta t, and then yt is that xt plus this error. And our observation errors then are the difference between the state and the observation. This sort of model where you just fit a linear regression, that would be, that's actually, a common thing to do. If you think about if you have a population count data and you want to know what the trends are, you just put a linear regression to it, and then you get the average trend. In this case, it's about a trend of 0. It's not increasing or decreasing. And then when we have the random walk model, we have this. Now we have that state is not a straight line, but rather it's a random walk. So this is what we estimate. And again, the observation error is the difference between this and this. Yeah?
How are you fitting a random walk? Just other parameters in random walk? I guess the trend parameter?
Yeah, so that you've got, it's xt equals xt minus 1 plus the u, the trend.
Okay.
So you got that one.
Okay.
And then you also need to estimate that variance. So how wiggly is this?
Okay.
That's going to be determined by the process variance.
Okay.
And then for your observation, you have your observation variance,
Okay.
which is how big do these errors tend to be,
Okay.
right?
Yep. Okay.
Okay, so you're going to have, the simplest version, you're going to have 3 parameters to estimate. We're going to do that in just a few minutes. Okay, so I already talked about this. These are the issues with citability, why we need to estimate those 2 variances. Okay, we talked about the process variance. Okay, so the observation variance is pretty simple to wrap your head around. It's just the difference between your estimated state and, it's actually the difference between the true state and the observation. We're going to estimate this, but you can imagine that, there exists some state. We just don't know what it is. Okay, so that's your observation error. Your process error is this. So this is just the state. Okay, the blue is that hidden state. Let's think of this as population size. This is the actual population size, is the blue line. We don't observe this. We observe this with error. Okay, we don't observe the truth. The process error is the difference between what you would predict the population size to be, given your value today. So what do you predict it will be tomorrow? And that prediction is based on the trend estimate. So here it's negative 0.02, so it's estimating that it goes down 2%. So you predict it will be here, but then actually it was here. So the difference between what you predict it would be and what it actually ends up being, those are your process errors. If that process error variance is very large, this will be very wiggly and tend to very quickly wander off. If that process variance is very small, it'll just tend to go up or down. Okay, so let's see this in action, how you actually would use this. I'm going to show an example of doing a population viability analysis for wild dogs in Africa, which are critically endangered. This is an example of what's called a count-based population viability analysis. And what you want to do is you want to fit to those data points. The data points are the wild dog counts between 1970 and 1991. And those counts have error. So we want to estimate what the true population size was, the red line. And from that, we want to get the U estimate, which is our trend. So remember, it's xt equals xt minus 1 plus the U plus the error terms. And that U is, on average, how much it's going down or how much it's going up. And so this says negative 0.54. That's a very steep decline. And then here's some sample projections using that and using the estimated process variance. So I'm just simulating the red line. And you can see it's all going down to 0 here. And then what you can do once you have those estimates is you can compute things like what's the probability of hitting a population size of 2, and at certain times in the future. This is the average. So what this is saying is that at 50 years in the future, there's a very high probability, about 50%, that it will hit a threshold, a population size of 2. And then you can also portray your uncertainty by looking at, this is in the future, and this is the population size. So this would be a 50% decline, 90% decline, 99% decline. And what you can say is this dark area is very certain, this is highly uncertain, this is who knows. So you can see there's a lot of uncertainty there. The green line is your, I think that's 80%, and the red line is the 95% confidence intervals. So you can see already here, it's like, who knows what's happening in 40 years. It's 0 to 1 that we would hit a population size of 2. So it's saying, it could be a 0% chance or it could be a 100% chance. But then you can take a whole bunch of plots that look like this, and you can see this was a 99% decline. On the order of that, somewhere that point is somewhere right around here. And what that's saying is that we're really uncertain about projections that are, about okay, I might do this. Is that so here? 0 to 1. Maybe it's up here. Okay, well, I didn't look at this carefully enough before I record the lecture. But basically what you can do is you can map out these regions where you are very certain about what's going to happen, and then regions where you're uncertain. So even though you might have a plot like that where there are parts where you're very uncertain, so you're very uncertain out here, you can be quite certain that nothing all that terrible is going to happen in the next, or you're not likely to hit a threshold of 2 in the next, say, 5 years. Okay, I remember what this is. So this is the uncertain region. So you're very uncertain about things that are very far in the future, but you're quite certain about things that are closer, and you can quantify exactly when your uncertainty starts going up. Okay. So why is it really important to separate these process errors and observation errors and get separate the variances and get a really good handle on what the size of these are? Well, the big reason is that it makes a really big difference in your projections if you assume a model with only process error or only observation error. This observation error only is your linear regression. So this would be a typical projection that you're going to do if you just fit a linear regression through these data. You did that, so okay, that's the trend, and then someone says, okay, well, what's the probability of hitting 2 out in the future? Or you're going to forecast, and you're going to say, well, that's very unlikely, right? This is what you would estimate. We've seen when we are simulating random walks, they tend to explode. And here what we've done is to fit a model that's only process error, but mixed in the observation error with it. So I said, okay, yeah, I know that it's a random walk. I know it's a population process. I'm just going to ignore that there's any observation error because I don't know what it is, and I'm just going to ignore that. If I were to do that, I would estimate that the probability of hitting low values with thresholds is much, much higher. The truth is somewhere, right, somewhere between these two, because the data have a process error. That is, the population size does fluctuate from year to year. We know that. But we also know that there's some observation error. Okay, you were saying, how do we separate these two? I'm going to give a real kind of back of the envelope answer, and that is that process error, or a random walk, and observation error, where that error is temporally independent, they have different temporal structures. And the algorithms will use that temporal structure. So if you had a random walk, if you just look at this, you can see with your eye that it's autocorrelated. And then look at the observation error, and you can see that, you can see with your eye this sort of temporal independence. And the algorithm is going to, like I said, it's going to be using that temporal pattern to help separate. Yeah?
It's perhaps important to think about that linear regression example you showed, right? On one extreme, it is just a straight line through the data. It's all observation error. So it would only fit observation error. And on the other one, you would have a random walk that just mapped onto the x's exactly. So, right, that's observation error only. And if we took away all the observation error and made all process error, the blue dots would be right on top of all the x's. So the algorithm is going to decide, okay, is it all one, all the other, or a mix? And oftentimes it's a mix that's the better fit. Not always. When we do things in lab, you're going to find out that sometimes you're asking it to fit both, and it will say, no, based on all the information you give me, it's only observation error, it's only process error.
And I mean, you can think about mathematically, if you look at those equations, you can write the likelihood of the model. Right, you can write the likelihood of that, and then you could write the likelihood of making this blue line be the black line. So those would be the two extremes, and then you could write the likelihood of the model that includes both of them, and you're going to maximize that. But the reason that those variances, those parameters aren't completely confounded is that those two models, the random walk model and the observation only model, they have different temporal patterns. They're not, when you just simulate it out, you can see they look really different. If they didn't, if they looked pretty much the same, then you would be hopeless. You'd never be able to separate them. because you're trying to, you're using models that can produce exactly the same kind of data. Okay, 2 more slides, and then we're going to jump in and start doing this. Okay, so I want to briefly go over the Kalman filter, because you're going to hear this algorithm mentioned when you're working with this class of model, but also if you were to read the help files for the ARIMA, you would see that they've mentioned the Kalman filter. And they mention the Kalman filter because they rewrite a lag-P ARIMA model. Actually, it's the lag-P ARMA model as this class, as a state space model. It's in matrix form. They write it as a state space model with hidden state and observation. And then they can use the Kalman filter algorithm, which is very fast. The algorithm works basically like this. It's a predict then update algorithm, and you start with at the beginning of your time series, and then you're going to predict the next time point, and then you look at the actual data that you got, and you update your estimate. So this is your prediction given your data up to time t-1, and then this is your estimate of your state. You're estimating your state, right? We have this hidden state. So we estimate what our hidden state is from our model, and then we look at what the data were, and then we're going to update that estimate. And then using that estimate, we're going to make a new prediction of the future. And then we look at the data that we actually got, and then we update that. And then we keep stepping through our data. And the nice thing about that is that if we want to make a prediction for time 4, all we need is the data from time 3. And we can make a new prediction. Okay. What else? Okay, so when you, let me go back here. So whenever you hear the word Kalman filter being used, what you should be thinking in your head is hidden state. So I have a type of problem where I have some observations, and there's this hidden underlying state, and the Kalman filter is going to estimate that blue line. It's going to give me that blue line. Okay, so let's jump in and start trying this. So if you go onto the website, you see I have the Univariate Example 1, 2, 3, and 4. And we're going to start with Univariate Example 1. Make this a little bigger. No. So once you open that up, let's just source that. Let's see here. There we go. Okay, great. Source it again. So the first part here, I'm just going to plot a line. And there I have a line, and I have some data around that line. And then we're going to estimate that line using a linear regression. So that's the next block of code. Okay, it's a really simple idea, right? Okay, there's just some line, and there's our data. And the red is our estimate of that line. You see it wasn't perfect, but we wouldn't expect it to be perfect. We've only got, what, 10 data points there? And now we're going to fit this with a hidden state model. Okay, so row 2 here. We have markers.
I think there's one on the
There's a couple on the floor there, just
In
on the
front
other,
of the
between
podium.
your left turn and your.
Okay, so you want to fit this as a hidden state model. You want to fit it as something that looks like this. X equals xt minus 1 plus u plus wt, and yt equals xt plus vt. So we need to figure out how to write that linear regression in this form. And to do that, we will have that that x1 equals the intercept plus slope. Those are our two parameters there. And then we have that xt equals xt minus 1 plus, what do we have there? The slope plus wt. So that is here what a linear regression looks like. This is the important part, that you see that it's this plus the data point in the past plus the slope. And the reason you need to recognize this is now you see how you're going to specify the model when you fit it. Okay, so now we are going to dive a little bit for 5 minutes into specifying the model for the Mars package. And the Mars package wants to know exactly what that equation there looks like. And let's go back here for a second. It wants to know, what is that B matrix? So look at that equation over there. What is that B? It's just a 1. And look over here, we specify as a 1. It wants to know what the U looks like. What is the U over there? Okay, that's slope, so we're just going to call it slope. It wants to know what the Q looks like. Well, that's something we need to estimate, so we're going to, well, actually, in this case, we're fitting a straight line, so that's just equal to 0. So let's see here, we've got a 0 there. Now we got to go to the Y. What does the Z look like? Well, it's just a 1, so we specify that as a 1. We don't have any A's there, so that's going to be 0. And the observation error, that's what we're going to estimate right here. So this model list is that equation right over there. It's specifying what all the parameters look like. And now we can pass that in to this function, which is going to fit this model list, and it's going to fit it to that data Y. So now, to get this to run, you have to be able to, install the Mars package. Let's go ahead and run this. So that's here. Run all of that. See what that looks like. Yep. So it worked. So the blue line was what came out of the linear regression out of the LM, and then the red line is what came out of rewriting that model as a state space model. Let's go forecast. Okay, that was the key bit. I'm going to do, yeah, I just want to go quickly do the next file. That's this one here. And this one is showing you the same example, same sort of example, but we're going to fit a random walk. Sorry, let's open up 3. Okay, this is what I wanted. Okay, so this shows you the example where, come on. Number 3 is showing you where you're estimating the hidden walk. There we go. Okay. So what we have here is this black line is the hidden walk here, and the blue line is what we estimate. And so to fit this model, what we do is we need to specify this. This is the random walk, but now we don't set this to 0. We don't set that variance to 0 because we want to allow that to vary. Remember, for the linear regression, we set that to 0, so it would be a straight line. We allow that variance to be there, and now it's a squiggly line. It fits that random walk. We have that, And then we have our measurement, which is just the XT with the error. And let's look at what that looks like in the R code. It's just translating one-to-one. We've got the mu, the u, that's our slope. We've got an initial value, you can ignore that. The key thing is here we have this v. Let's go back here. Right, we have that v, that's 1. We have that, that's what we're estimating. We have the q, that's what we're estimating. See, it's right over here, we're estimating a q. The z is 1, we set that to 0, and this we're estimating. This is exactly the process that you're going to be using for much more complicated models. You're just going to take this, and you're going to start working through, bit by bit, what these look like. And then you can fit them here, and boom. And this is what it's estimating. It's estimating that the observation error variance is 0.11. It's estimating the slope is 0.4, and then it's estimated the process variance. All right. Okay, let's finish there. Go ahead and run through those 4 scripts. That's going to give you a lot of practice, just kind of running through these, looking at the code. It's going to produce a variety of plots for you that you can sort of look at and think about, particularly these right here. This is showing you an estimated forecast using your estimated parameters, and the red is what the true forecast should have been. And it's going to show you what those forecasts look like when you have a process error only model and an observation error only model. And you'll see how very different they are.